Assume we have an enclosure consists of two surfaces. So let's say this is surface 1. This is enclosure that we have. So surface 1 at temperature T1 and surface 2 at temperature T2. And we are going to find out the rate of the heat transfer, the exchange of heat transfer between these two surfaces, Q1, 2. So if I start from either of them, let's say from EB1, we have the surface resistance, R1, then we reach to the point J1, then we have a space resistance, R12, here point J2, and then again we have the surface resistance because of the surface 2, which is R2, and then we have EB2. Now Q12 is equal to Q1, let's say this is Q1, this is 0.1, then this is 0.2, equal to minus Q2, and it's going to be the difference between them, EB1 minus EB2, divided by the surface resistance of R1, space resistance of R12, of R2. Now if I just replace the values for them, Q12 would be sigma T1 to the power of 4 minus T2 to the power of 4, divided by surface resistance for surface 1 is 1 minus epsilon 1 A1 plus the space resistance is going to be 1 minus A1 F12 plus the surface resistance for the surface 2 would be 1 minus epsilon 2 A2. So this is going to be the exchange of the radiation heat transfer between these two surfaces. So for example, let's look at an example here. Let's say we have two large parallel plates. Plate 1 and plate 2. Two large parallel plate, A1 is equal to A2, and these surfaces do not see or do not strike themselves by the radiation. So F12 is F21, F11 plus F12 is going to be 0. They don't see each other, sorry. It's going to be 1. So from here, F12 is going to be equal to F21 equal to 1. And Q net between the two would be sigma, let's say this is T1 and T2. T1 to the power of 4, T2 to the power of 4, divided by 1 minus epsilon 1 A1, plus 1 minus 1 over A1, F12, 1 minus epsilon 2 A2. Now, the areas are going to be the same. If I divide that, so Q net over the area, flux is going to be sigma T1 4 minus T2 power of 4, 1 minus epsilon 1 plus F12 is 1 plus 1 minus epsilon 2 over 2. And that's going to be sigma T1 4 minus T2 4, 1 over epsilon 1, epsilon 2 minus 1. Since there are long cylinders, we can assume the top and bottom surfaces are negligible here, or they don't really contribute. So let's say if this is the one of them and this is the other one, we can get rid of those ones. So F13, 14 is going to be 0. If this is 1 and this is 2, F12 is going to be 1, but F21 wouldn't be 1. And if I write Q net here, between the two is going to be sigma T14 minus T24. And the resistance that exists between them, 1 minus epsilon 1 A1 plus 1 minus A1 1 2 epsilon 2 A2. And this is 1, so this will be sigma, and if I multiply both sides by A1, sigma A1 T14 minus T2 to the power of 4 divided by 1 over epsilon 1 minus epsilon 1 over epsilon 1 plus 1 plus A1 over A2 1 over epsilon 2 plus 1. So this is going to be sigma A1 T14 minus T24 divided by 1 over epsilon 1 plus R1 over R2 1 over epsilon 2 minus 1. Now, if it happens that we have two cylinders that R2 is much larger than R1, it's like examples of that is a wire in a large pipe, or the other one could be small diameter pipe in a large room or apartment. So if R2 is much larger than R1, then we can say R1 over R2 is approximately 0. Then from here, Q net is going to be approximately sigma A1 epsilon 1 T14 minus T2 to the power of 4.